Good evening to all of you. Good evening, wisdom. So, we are taking this extra lecture, and in this extra class, we will talk about fluid mechanics, the dynamics part. Earlier class, if you remember, we talked about the statics. Statics is all about what happens when a fluid remains stationary, when a fluid is not moving. If a fluid is not moving, then all those situations comes under the category of fluid mechanics, the statics part. And two fundamental principles they operate all the time when the statics is there, and that is Pascal's law, that is the pressure remains undiminished throughout the liquid, and Archimedes principle. Now, in this class, we are going to talk about dynamics. Dynamics means motion. What happens when fluid is in motion? What happens to its pressure, velocity, etc.? So, the two principles which are vital for fluid dynamics are equation of continuity and Bernoulli's equations. So, these are the core of today's this lecture. And towards the end, we will talk about a little bit of viscosity and turbulence. So, what is equation of continuity? So, as the name suggests, it talks about continuous, something which is continuous. It talks about a continuous flow or something which does not abruptly stops. So, for example, if you have a fluid flowing through a pipe, so I am showing you a pipe whose cross section has been marked. A fluid is flowing through it, irrespective of what height or what orientation the pipe has. The fluid is just flowing. Now, at some point, let us say the cross section of the fluid is A1, cross sectional area, and at some other point, let us say that the cross sectional area is A2. In this case, A2 is shown as smaller than A1. That means the cross sectional area is decreasing and the tube is tapering off. A reverse can also happen. For this discussion, that doesn't matter. As long as the area is changing, we can have take the discussions forward. Let us assume that velocity at this point is v1. Velocity of the fluid at this point where we have taken the first cross section A1 is v1. And now we ask this simple question, that would it have the same velocity at point 2 or will it have different velocity? And that is what we are trying to figure out. So for an argument's sake, let us assume that the velocity at this point is different, that is v2. And let us try to explore. If our argument is correct, then we will get v2 as different than v1. And if our argument is incorrect, then we will get v2 as same as v1. So for the time being, we can assume that velocity here is v2. Now, if the velocity here is v1, the question is, in a small time interval dt, how much would be the displacement of this cross section of fluid? So the displacement of this cross section of the fluid in time dt would be a quantity called v dt, or in this case it will be v1 dt. Remember, velocity is distance upon time, so distance is velocity into time. So this distance, small distance traveled in a small time interval dt, at this point will be v1 dt. Okay. In a very similar way, the element over here will travel another small distance and it is called v2 dt because the velocity here is v2. So, how much volume is entering the tube at a given instant? So, the volume that is entering the tube in small time interval dt is going to be the volume of this cylinder. Just imagine this entire cross section was here when time started. After time dt, the cross section has moved to this position. So that means in time dt, if I ask how much is the volume of fluid entering the tube, then it is the volume of this small little cylinder or disc, whatever you call it, whose area is A1 and whose thickness is V1 dt. This is the volume of the liquid that enters the tube in time dt. So the volume entering the tube dV1 can be written as the volume of this disc or cylinder. The volume of this disc or cylinder is cross-sectional area into thickness, that is A1 into V1 dt. The entire cross-sectional area into V1 dt. In a very similar way, volume leaving the cylinder can be computed here, and it is the volume of this cylindrical disc. This is going to be A2, which is the cross-sectional area, into thickness, which is V2 dt. So it is going to be A2 V2 dt. So this is the volume, amount of volume leaving the cross-sectional area. Now the question is, how much is the mass entering? So now that's a tricky question to answer. I know the volume and I know that density can be used to get the mass. In morning lecture we checked how do we define density. Now let us say that liquid has the density rho and therefore the mass entering can be equal to rho A1 V1 dt. But there's a catch or there's a trick situation here. And what is the trick situation? And the trick situation is the density going to be the same for the entire liquid or entire fluid? Now you will find that this is not an easy question to answer. For some fluid, yes, density may remain constant. For some fluids, it may not, especially for gases. They may tend to accumulate at some corners. Some gases, they tend to go down under their own weight. So it changes. Most of the normal day-to-day liquids, oil, water, etc., density does not fluctuate under normal operation. But under special circumstances, like if you have a very high pressure, etc., the density can change. So that is a dicey situation. We would like to keep it simple. For the time being, I'm assuming that the density remains constant throughout the pipe. Now, if the density going to remain same throughout the pipe, then such a fluid is normally referred as incompressible fluid, a fluid which cannot be compressed at any point. So an ideal fluid or an incompressible fluid has been assumed. So if rho is the density at the entering, rho will remain the density while leaving, and therefore the mass leaving will be the mass of this cylindrical disc, which is density times the volume of that disc, A2 V2 dt. Now, suppose the fluid is flowing through this pipe at a very steady state. There is no change in the rate of flow. In that case, the amount of mass that enters has to be equal to amount of mass that is leaving per unit time, or maybe in time dt, whatever interval, time interval you choose. The amount of mass entering has to be equal to amount of mass leaving. Now think about it, what will happen if this is violated? So if this is violated, that means let us assume that more mass enters and less mass leaves. Then what happens? So if more mass enters, you will find that the density inside this section of the tube will go on increasing. While if the more mass leaves than what enters, then the density will go on decreasing. Now you can see this will violate our assumption that the liquid is incompressible and the density remains same. So remember, that is a very important assumption, because otherwise things will break down. That density remains constant. So if density remains constant, then in a steady flow the total mass in the tube is constant. That means amount of mass entering the tube dm1 has to be equal to amount of mass leaving the tube, that is dm2. Therefore, I can equate the right hand side of these two equations, and I will write rho a1 v1 dt is equal to rho a2 v2 dt. dt and dt will cancel, rho and rho will cancel. All you are left with a1 v1 is equal to a2 v2. Now this equation is normally referred as equation of continuity. All it says that the amount of fluid entering in a given channel, flow channel, in a given time has to be equal to amount of fluid leaving the same channel in the same amount of time. So A1 V1 has to be equal to A2 V2. Now this has important implications. Remember, one implication we have already discussed, that this is possible only if the density is constant and the fluid is incompressible. You cannot compress the fluid. The second implication is, look at the product. The product A into V is constant. Remember, point 1 and point 2 are chosen arbitrarily. I have chosen point 1 here and I have chosen point 2 here, but I could have chosen point 1 and 2 anywhere else. Like 1 could have been here or here, and for that sake 2 could have been here or maybe here. So these 2 points are arbitrarily chosen. What does it mean? It means that AV product is going to be same for all the points in a flowing fluid. That means the product of cross-sectional area and velocity is constant always for a fluid in a flow, in a channel. What does it mean? It means that if area decreases, and since the product has to kept constant, the velocity increases. If area increases, the velocity decreases. So the velocity can be controlled by the diameter or the radius of the pipe. This is very important. Many of the examples you can draw from real life for this one. If you have gardened, if you have done gardening, if you have given water to the plants with the help of the pipe, or if you have used a piped water to throw water in a lawn or anywhere, then you know that if you have to take the water stream at a larger distance, you close the mouth of the pipe by half. So why, when you close the mouth of the pipe by half, why does the water go to a larger distance? It's simple. When you are closing the mouth of the pipe, you are reducing the cross-sectional area. The equation of continuity demands that the velocity has to increase so that the product remains the same. So the water comes out with a larger velocity from the pipe, and therefore it can, as a projectile, it can go larger range. The other examples are the showers used in the bathroom. So if you have a shower, you will feel intuitively that the flow of water is much faster from the shower holes than from the tap. The reason is again one of the same. Since the shower holes are very tiny, the water appears to be coming very fast from it. The area decreases, velocity increases. Another example, your normal kitchen tap, bathroom tap, all you do is just close its mouth by half with your thumb, and you will find that the speed of the water increases quickly. It becomes doubled if you close half the mouth, and therefore the equation of continuity can be seen working in your day-to-day life. What happens if fluid is compressible? So if the fluid is compressible, generally then this equation gets an improvement. You have to multiply by, the density term does not cancel out. And you have to multiply by rho 1 on this side and rho 2 on this side. Remember, when you derived this equation, we cancelled out the density. It will not. So then the relation between area and cross-sectional area and velocity does not remain so linear, because density also plays a role. The other term that we will normally encounter while solving the problem is volume flow rate. Volume flow rate is defined as the volume of water flowing per unit time. So we have seen it earlier. It can be defined as dV by dt. So dV by dt is nothing but area into velocity. So this term, this product is also called as the volume flow rate, and when equation of continuity says that this volume flow rate remains constant. Now if you know volume flow rate, you can get mass flow rate as well. How? Very simple. You take the volume flow rate, multiply by density, you get the mass flow rate. And that brings us to the famous Bernoulli's equation. You know that a storm has hit Chennai, South Chennai today, yesterday and today, and a lot of destruction happened. So I ask you a very simple question, that why strong winds of a storm create such destructions on homes and buildings and roofs? The principle or equation that is responsible for that destruction is Bernoulli's equation. You must have seen the destruction caused by the storm in all newspapers and news channels today. Let's try to understand Bernoulli's principle and Bernoulli's equation, and then let's try to see how we can use this to explain the destruction caused by the storm. Here is the Bernoulli's principle. The net work done on a fluid element, when I say a fluid element, it's an infinitesimally small element. So net work done on a fluid element by the pressure of the surrounding fluid equals the change in the kinetic energy plus the change in the gravitational potential energy of that element. It is not written, but it is understood. So if you look at it exactly, what does it represent? If you look at it carefully, you will find that it is nothing but a little modified form of work energy theorem. It is conservation of work and energy. Whatever work you do, it is used either to change the kinetic energy or to change the potential energy. Who is doing the work? The external pressure is doing the work. So let us try to understand this little bit deeper. Again, I have a drawing which is similar to the last section. In this drawing, I have a tube which is in general can be uh, decreasing in or narrowing down or tapering down. I again assume a fluid which is incompressible. The fluid does not compresses. I will make two more assumptions which are important. And one is the fluid is irrotational. That is, the fluid does not rotate. If you go to higher classes of physics, you will study about the rotational fluid and rotational dynamics more in detail. You are going to talk about the curl or divergence and curl, of course, curl of a vector field, and then you will learn more on rotational aspects of fluid. At this level, at FYBSc level, at 11th, 12th level, we simply ignore the rotational component. We assume that the fluid is irrotational. Remember, because if it rotates, then some of the energy will go as rotational kinetic energy, which we don't want to deal with right now. So the fluid is irrotational, and we also assume that no energy is lost in friction. Now, that is not always true. The fluid does have viscosity and it does have frictional effects. We are going to talk those effects towards the end of the lecture. So, for the time being, when I'm looking at this or discussing at this principle right now, we ignore these two concepts, and that is rotation and viscosity or friction. Okay, so let's have things which are straightforward. I have 2 points in the fluid. This is first, this is second. I take a cross section here. Cross section is V1, sorry, A1, and the speed of the fluid element is V1. We will take cross section here A2. We show that the cross section decreases, so the velocity increases. So the equation of continuity demands that. Then this element is at a height y1 from the reference point. This element is at a height y2 from the reference point. So as the element moves from this position to this position, you can see that it gains a height from y1 to y2. This displacement on time dt is ds1. The volume of this element is dv. This displacement is ds2. Volume of this element is dv. Remember, everything has 1 and 2 labels, but dv does not have 1 and 2 label. Why? The reason being very simple. dv does not have labels because we have just discussed that the equation of continuities says that dv by dt remains constant. That is, the amount of water flowing per unit time is going to be constant. So dt is same, so dv is going to be same. So how much is this displacement ds1? So we have seen it. If velocity is v1, then this is v1 dt, and the displacement over here ds2 will be v2 dt. So how much is the volume flow? The volume will flow here is the volume of this element dv here is cross sectional area into thickness. So A1 ds1, and the volume of the element here is A2 ds2. So these are the volume of the two elements. Force at both the ends. So we assume that the pressure here is P1 and pressure here is P2. External pressure here is P1, here it is P2. Now if the pressure is P1, area is A1, then the force is P1A1 at this point, while the force here will be pressure into area at this point, which will be P2A2. So these are the forces at both the ends. So now I know my force, I know my displacement, so I can find how much is the work done. So my work done by external forces is force into displacement at this end, force into displacement at this end, but you can see that they are working in opposite directions, so with a minus sign, and that is the net work done by the external forces. So the net work done is P1 A1 ds1 minus P2 A2 ds2, but look at A1 ds1 or A2 ds2. What are these parameters? So A1 ds1 and A2 ds2 are my dV. So I can put it in this equation. A1 ds1 I can put dV, A2 ds2 I can put dV. So I'll get P1 minus P2 into dV. So this is the net work done when by external forces external to this element as it moves from here to there. What is the Bernoulli's equation then? How do we derive? So let us look at the other aspects of the element. What about the kinetic energy of the element? Now you know kinetic energy is half mv square. I know the velocity v1. What will be the mass of this element? The mass of this element will be volume into density. Now how much is the volume? A1 ds1. So this is the volume. Density is rho. The product of two will give me the mass. So half rho A1 ds1 V1 square. This is the kinetic energy of the element here. When the element reaches here, the velocity becomes V2. So the kinetic energy will become rho A2 ds2 V2 square. So what is the change in kinetic energy? Simple, I can take final kinetic energy, subtract the initial kinetic energy. There I know that A1 ds1 or A2 ds2 is my dV. So I can substitute in this place my dV, which will come out from both the terms. Rho is common, 1 by 2 is common. Only thing left is V2 square minus V1 square. So that is my change in kinetic energy. Please keep a note of this. What is initial potential energy? So potential energy as we know is mgh. So here the element mass is dm. So it is dmg, and instead of h we will have its height y1. But dm is again rho into dv into g into y1. So this is my initial potential energy. What will be final potential energy? So you apply the same principle at this point. So you get rho dv g y2. What is change in potential energy? The change in potential energy is final potential energy minus initial potential energy. So once you take that change, you will get du as rho dv g. These three terms are common. Y2 minus y1. Final position minus initial position. So this becomes the change in the potential energy. Okay, so we now got work done. We got the change in kinetic energy. We got change in potential energy. But who is bringing this change in kinetic and potential energies? Obviously, the external work, and therefore I can write my energy equation as dW is equal to dk plus du. The external work done will change the kinetic energy as well as the potential energy, and therefore the three equations, one here and one previous one, can be related in one equation. So let us do that. So work done was P1 minus P2 into dV, and dk is half rho dV V2 square minus V1 square plus rho dV G Y2 minus Y1. I can cancel out dV at all places and it will get simplified quickly. And then I can take all the terms with suffix 1 together. So P1, V1 and Y1. Remember, these two are negative. When they go to left side, they will become positive. P2 is negative, it goes right and it becomes positive. V2 and Y2 are positive. So once I segregate my terms, I will get all the terms written over here with one suffix, that is pressure at point 1 plus potential energy at point 1 plus kinetic energy at point 1 has to be equal to pressure at point 2, potential energy at point 2 plus kinetic energy at point 2. But do remember, after the cancellation of dV, these terms, this one, this one, this one and this one, are not strictly the kinetic energy or potential energy terms. They become what is called as energy density term. Once you cancel out dV, then this is nothing but the potential energy per unit volume, because you have divided by dV. This becomes kinetic energy per unit volume. Now remember, the point 1 and point 2 are arbitrary in the pipe. If you remember the pipe that we had chosen, 1 and 2 were chosen arbitrarily. You can take any 2 points as 1 and 2. What does it mean? It means that the sum of these three quantities has to be true for, or the sum of these three quantities has to remain conserved for any point in the pipe until the conditions are satisfied. What are those conditions? The fluid is incompressible, fluid is irrotational, and fluid is non-viscous. So if those three conditions are satisfied, then the sum of these three quantities throughout the flow remains conserved. And that is what is called as Bernoulli's equation. That is, the pressure plus potential energy density plus kinetic energy density, the sum of the three remains constant. Now at this point we can think of interesting corollaries. Let us say that a flow is happening at the same horizontal level. So if the flow happens at the same horizontal level, then y1, rho g y1 and rho g y2 will cancel out because the horizontal level is same. Y1 is equal to y2. Then P plus half rho V1 square has to be equal to P2 plus half rho V2 square. Now obviously as you go from P1 to P2, suppose if your pressure increases, then your velocity has to decrease. So a decrease in velocity results into an increase in pressure. This is what leads to the destruction during storms. When the storm hit a country or hit a landscape, then any roof, the wind blowing over the roof is generally at a very high speed. While under the roof, the winds are, or the wind is or the air is static. Its speed is very less compared to the speed outside. So what happens? Horizontal level is nearly the same, but as the velocity is less inside the roof, the pressure becomes high. So inside the pressure becomes very high. The outside pressure remains low because the velocity is high. Sum total of P and half rho V1 square must remain constant. As a result, there is a huge force work on the roofs from the inner section to the outer section, and they can be blown away. If they are not fixed very rigidly, the roofs are blown away. In rural areas especially, this causes huge destruction. So we have seen some example like water pressure in your home. So you would, if some of you are staying at the, most of the buildings have water tanks at the top. Suppose if you are staying at the top floor or second floor from the top, the water pressure in your home is generally very less. If you are staying at a ground floor, then the water pressure will be high. Again, question is why? Answer is now you are living at two different heights from the ground level. So if you look at Bernoulli's equation once again, as if height now you forget the v square term. If height increases, pressure decreases. So if you are living at a larger, at a higher floor, your height from the reference level increases and the water pressure decreases. If you're living at a ground floor, generally in your taps, the water will come at a very high speed. Speed of efflux, we are all familiar, very beautiful experiment. Many of you have seen that if you have a container filled with the liquid and if you puncture holes at different heights, then you know that the fluid coming out from different holes does not hit at the same place on the ground. One coming out at the lower part goes farther, while one coming at the top higher portions will fall down earlier. Why does that happen? Because the speed with which the water comes out is different at different heights. This again can be shown or proved using the Bernoulli's equation. The venturimeter is a device which is used to measure the flow of a fluid, speed at which it is moving. We will take up maybe one problem on venturimeter, but most of you have seen or have studied it in your 11th standard. So right now I'm not going into the detail. Lift of an airplane. Just now I explained how the building roofs are blown away in a cyclone or a storm. The lift created in an airplane is in a very same way. Just that the wind doesn't blow, but the airplane takes a very high speed. When the airplane takes a very high speed on the runway, then this is the cross section of the airplane. The wind blowing below are generally uh, are relatively at a lower speed, while the winds which are blowing from the above, they are generally at a higher speed because of the shape of the wings. The wings are flat at the bottom, while the wings are curved out at the top. So because of this, the air has to travel a longer distance in the same time, and therefore the velocity drops and the pressure differential comes into existence. It has to travel longer distance in the same time, sorry, so velocity increases and the pressure drops. So lower side velocity is less, pressure is more. Upper side velocity is more, pressure is less. Because of this pressure differential, an upward force works, which is responsible for the takeoff. The airplane has to move or need to move at a certain speed for this to happen. Now we go to the last section of today's lecture, and that is viscosity and turbulence. So this is a viscous fluid, lava. Many of you we have not witnessed because India does not have any active volcanoes, at least for now. In the earlier history, there had been volcanoes, not in the era of written history, but long back. For example, the entire Sayadri range is a creation of volcanic eruptions. But many part of the world still see some of the volcanic eruptions here and there. The lava is a thick, viscous fluid. In our day-to-day life, water is a very thin fluid, water and milk and any other derivative, but oils are little thicker. What other examples we have? Maybe honey. Honey is much viscous than both oils and water. The other fluid is the glycerine, which is also available easily over the counter in a good medical shop, where the viscosity is very high. Depending upon the viscosity and some other parameters, the water flow can be streamlined like here, or it can be turbulent like here. But that's a separate discussion. I'm just giving you a hint. You know that it relates to Reynolds number and speed, etc. But we are not going into those domains right now. So this is how the viscosity works. Typically, whenever a liquid flows, so far our assumption was there is no viscosity and the cross section of the flow remains uniform. But that is not actually the case. In a real world, the walls are static and the layer of the liquid that sticks to the wall, it also becomes static. Its velocity becomes zero, while the layer of the liquid which is in the middle of the pipe has the maximum velocity. So as you go from the walls of the pipe to the center of the pipe, the velocity layer by layer goes on increasing. And remember, I'm talking about layers because it is a cross section. In practice, this is a transverse cross section. If you have a longitudinal cross section, then all these layers will be cylindrical in nature, one into other. So at the center, the speed is maximum, and as you come from the periphery towards the center, then a velocity gradient exists. So one layer, if here the velocity is v1, then here the velocity v1 plus delta v. Here the velocity v1 plus delta v plus delta v. So the velocity gradient exists, and because of these, if you take any layer, then this layer will try to pull the faster moving layer in the backward direction. So this layer will try to pull this layer in the backward direction, while simultaneously this layer will try to pull this layer in the forward direction. So there are friction between different layers of the liquid, just like friction happens between the solids. You know that the coefficient of viscosity or this force of viscosity is given by A eta dV by dr, where A is the area of area of any layer, eta is coefficient of viscosity, and dV by d small r, dV by dr is the velocity gradient. So that is a Newton's law, Newton's formula for viscosity. Just remember that formula for your exam, where there is no derivation or anything like that. It is largely an empirical formula. Viscosity defines how the motion of spherical objects happen, and especially the motion of a ball which is spinning or not spinning. And it creates a very strong role, it plays a very strong role in sports. If you saw the, if you are tennis fan, then the recent match between Nadal and Djokovic, if you have seen, then you have seen that how Djokovic's top spins, they are so effective in dropping the balls on the net. So all this is happening because of the viscosity effect and Bernoulli's principle. So let us try to understand. If the ball is moving straight, then nothing great happens. But if the ball is spinning and also moving to the right, then when the ball is spinning, the ball drags the air flow along with it. Remember, in my diagram, the ball is moving to the right side and it is also spinning. So the immediate layer of the air which is to the ball will be dragged along with the ball in the circular fashion like this. Now when that happens, the two things happen simultaneously. The airflow speed on this side of the ball drops. It slows the air on the upper side if the ball is spinning this way in my diagram, because the air is carried along with the ball in the direction of the motion. On the lower side, the air is carried in the opposite direction to the motion of the ball, so the relative speed increases. Since the relative speed up on the higher side or upper side decreases, there is an increase in the pressure. So a pressure increases here. Since the velocity decreases here, since the velocity increases at the lower part, the pressure drops. And because of this pressure difference, it gives a downward push to the ball. And this is what happens a typical topspin tennis shot or a typical topspin shot in table tennis. So ball spins, goes up and drops very quickly. Some of the cricket spinners also are able to achieve this one. In cricket, more other effects happens like swing of a ball. So one side is rough, one side is smooth. When the ball is thrown, before it bounces, I'm not talking about the swing on the seam, but I'm talking about the swing in the air. Before it bounces, on the rough side, air is dragged along with the ball. So the relative velocity decreases and pressure increases. On the smoother side, the velocity of air is higher. So the speed increases, relative speed increases, and pressure decreases. As a result, the ball will deviate from the rough side where the pressure is high to the smoother side where the pressure is low. Now, if a fast bowler utilizes this, if a fast bowler who is bowling at a speed of 140 km per hour plus speed, and most of the fast bowlers do that, some even go to 160, 170 km per hour speed, and even if the ball deviates by 2 to 3 inches in air, it becomes a very difficult ball to be tackled by the batsman. And considering the fact that the bowler can hold the ball in either way and swing it either inside or outside. And plus, if there is a little help from the wind or the pitch, the bowling can become lethal. So again, a lot of physics is involved there. I would like to end this lecture with this video. This is Roberto Carlos, who has been tackled foul and he has been given a free kick. And he takes a beautiful free kick, and you can see how the ball curls in air, the way he kicks. This is a match of Brazil against England. I don't remember which World Cup it was the part of, but I had seen it live. And there we had a famous English goalkeeper, Peter Shilton, who remained standing to this shot, couldn't do anything. So in slow motion, observe how he kicks and how the ball turns. You can see that this is the direction he is hitting, and then how the ball curls in air. And he was a bit fortunate that towards the end it hits the pole also, giving no scope whatsoever to the English goalkeeper. He's the famous English goalkeeper who was playing his last tournament, and I think this match happened to be his last match, last international match. He took a retirement after that. So I will just play the video again. Here is the foul. Okay, so with this, we stop this lecture. We have done the most of the theory part of this chapter. Next lectures, we will take some of the review questions and problems. Thank you.